is really the most straightforward way of doing for first order molecular dynamics. You start from ionic position, do a DFT calculation, apply Hellman-Feynman theorem, get forces, move the atom, and repeat the procedure again to just get your electrons and your forces and sample your potential energy surface. It is not as trivial as I make it sound right now. You need to know a lot of technical details, and again, these will be covered tomorrow. But just assume for the moment that we're all very much versed in all these technical details. We know everything, and then we apply this to some problems. And now I want to give you examples. So before I go to the examples here, let me just point out one thing. That because at each step of what I call the ab initio molecular dynamics, you have to solve the electronic problem and derive forces from the electronic wave function. The number of atoms that you are able to deal with and the length of your simulation time is very different from what you can afford usually by doing classical MD. These days, not on any laptop or workstation, but with moderate-sized computers and with reasonable range potential, you can deal with millions of atoms, and also you can deal with nanoseconds for classical MD. Usually, ab initio MD, we are limited to the hundreds of atoms and picoseconds. But please, when we talk about what can be done with an ab initio molecular dynamics, always remember that the key variable is really number of electrons. Okay? If you simulate sodium with only one valence electron, very different than simulating, fluorine or oxygen with 6 valence electrons. And so it's not the number of atoms; it's really the number of electrons that actually does matter when we talk about molecular dynamics. But roughly, to have an idea, here millions of atom nanoseconds, and here you are down to hundreds of atoms picoseconds. So different kind of system, different kinds of time scale, and also different kind of error bars. So one comment about another way of doing first principle calculation using forces derived from, for example, quantum chemistry. And this is an example that I mentioned at the beginning of the lecture. So you may think of fitting a potential to actually quantum chemistry calculation for a small set of a system representative of the system that you want to simulate. And then use the potential to simulate your system. So here is an example of a potential derived for water fitted to very accurate quantum mechanical calculation of water cluster, and then used to simulate liquid water. This is a GeoBar, oxygen-oxygen correlation function. This is experiment. The black line and the maroons line, the brown lines are obtained with different type of fitted potential. And you see that you can actually reproduce, at least with some of the potential, the experiment quite well. You have, so there are different curves here, and the blue curve is fitted only to a certain amount of data. And the point here that the authors were making is to just show that you need actually to go to a very accurate fit to reproduce the results quite well. Okay, you may want to do this, and this may work, but what happens that when after you have fitted the potential and you have this beautiful potential for water and you want to put something in your water, you want to put an ion, you want to put a nanoparticle, you have to start it all over again, right? So if you really, what you want to simulate is water, you may want to fit your potential to quantum chemistry calculation, and you may end up, this is questionable by the way, but you may end up with an accurate potential, but the very minute that you want to change your system and put something in your water, you're lost again and you have to restart your fitting procedure all over again. So I am quite convinced that actually the way of doing first principle MD by computing forces for the configuration that you want, the system that you want at each step is much superior in generality and transferability than just fitting potential to first principle calculations. Let me this is, of course, my personal take on that. Okay, examples. Before I go through examples, are there questions? Okay, so we have half an hour, right? Okay, so I choose 3 types of examples. One is use of first principle MG to look at phase diagrams, a very simple system. One is liquids on surfaces, and the other one is nanostructures. The examples that I will present are from my own work, just because I know those better. I would like to make sure you understand that actually there is quite a large community of people, actually I would say all over the world, applying and using first principle molecular dynamics for systems similar to that, or also other systems. And again, the examples are drawn from my own work, but by no means are representative of the whole work that is going on in the community, which is really kind of exploding, and there are many, many problems that these days are being tackled and also solved by using molecular dynamics. But hopefully they will give you an idea of some of the questions that you may ask by using molecular dynamics, some of the answers that you get, and also at the end I want to point out open problems. Okay, so phase diagram of elements. Here, this is a cartoon of a pressure as a function of temperature for a generic substance. You have, of course, phase line, and you have, for example, here, melting line of this substance, and liquid gas transition. And if you're not familiar with the state of the art in determining phase diagram of elements, actually you may be surprised if you look at the literature to know that both theoretical but also experimentally, even for very simple system like first row element, there are a lot of unknowns out there, and there are a lot of phase coexistence line and, for example, melting transition that are not understood and are difficult to determine experimentally, and also theoretically have been very challenging to determine. And here I've just pointed out some of the questions for some of these elements that have been out there in the literature for a long time, and some of them still are. For example, for carbon diamond, there have been a question out there for a very long time about can we really melt diamond under pressure, or diamond will always transform to some other structure before melting when you put it under pressure. Can we have a liquid ground state at 0 temperature and high pressure for hydrogen? This is still a very controversial issue, whether hydrogen is really solid under pressure at 0 temperature or not. Again, interesting phenomenon occurring in oxygen at high pressure, which can possibly be described as a spin glass of oxygen molecules. Boron, there is a discussion in the literature about whether actually boron is an element with a crystalline ground state or not. And the phase diagram of water has been one of the most controversial that actually among the simple substances in the literature, I would say, in the last 20, 30 years or so. So let me tell you about what you can do using molecular dynamics to answer some of these questions or to address some of these issues. So one way to use the molecular dynamics to actually determine melting lines is the following. It's the way that we and many others have used is the following. So you take the system that you want to simulate. For example, you want to simulate the melting of diamond or melting whatever, a system, and you prepare it in a solid form, here the red part, and then you do a separate molecular dynamic simulation. You use all the techniques we talked about this morning. You heat up your system, you melt your system, and you prepare it in a liquid simulation. Then you use the technique we talked about to do constant pressure molecular dynamics, and you set the pressure of your solid and your liquid, and you put your solid and liquid in contact with each other, and you let the system go. And at different pressure, so you choose the pressure, you see the phase that wins. You look, and for example, here you simulate at a certain temperature, 800 K. You simulate for a certain time. This is a very short time. This was a system which was actually quite fast to simulate. And you see, and for this system, at this fixed pressure, at this temperature, the phase that wins is the solid. Then you go at another temperature, same pressure, and you see the phase. And by win, I mean the phase which turns out to be the most stable when the system reaches equilibrium. By doing this, actually, you are able to determine at a certain temperature whether your system is a solid or liquid. And if you do this for many different temperatures, you may be able to bracket the melting temperature of your system. So you see, we have a certain pressure, and we look at the temperature here, T1 of 800 K, whether the solid is more stable than the liquid. We do this for another temperature. And we have identified a situation where here we have the solid, which is more stable, and here we have the liquid. And then we go and do the same simulation in between 800 and 900 K. And then finally we get to bracket the melting temperature of the system.
Okay, so how can you determine if it's solid or diffuse?
Yes, a very good question. So in order to determine whether it's a solid or a liquid, you have to use different criteria. So first of all, you look at the diffusion coefficient, whether the system is diffusive or not. This may not be your only criteria, because sometimes there are, depending on what you are simulating, but your liquid may be very viscous, and so the diffusion coefficient may seem to saturate and become very small, but still the system may be a liquid. So you have to have a set of criteria: diffusion coefficient, G of R, and also in some other cases, some other electronic properties we were looking at, or other transport properties. So you use a set of criteria that consistently tell you whether the system is a liquid or a solid. But for the system that I talked about, and I'm talking about here, like carbon, hydrogen, and also oxygen, actually, the determination of whether the system is a solid or a liquid is quite simple, because in all liquid state that we have looked at, the diffusion coefficient is actually quite large, even close to the melting line. For water, for example, it's much more difficult to determine that. And when you do this simulation, you have to check the usual thing, that the size effects are under control, that the simulation is long enough, and so on and so forth. So if you do this, for example, this is a melting temperature as a function of pressure of hydrogen. And these are the simulation points that we have done. See, these triangles here are all simulation that we have done to finally bracket the melting temperature. These are experimental results. So I'm showing you two cases. One is hydrogen, and the other is carbon in a minute. And I've chosen them because these are actually two examples of a system for which the simulation was done first. A prediction was made, and in particular in this case, a prediction was made about the fact that there is a maximum in the melting line of hydrogen, and the experiment confirming the simulation about the existence of this maximum were done later on and actually confirmed. They were done in particular in Silvera's group at Harvard a couple of years after the simulation. And it's a nice example of the simulation that has predicted a phenomenon that then has been actually indeed verified experimentally. So why do we care about a maximum of on hydrogen melting line here. Well, one reason is that if it's true that there is this maximum, and it looks like it has been found experimentally, and then the melting line turns around like that, if you extrapolate, it actually may mean that there is a region of the space diagram of hydrogen where you have a liquid at a 0 temperature. And this would be a very exotic state of matter, and this would be, of course, a very new thing that you don't find basically with any other elements. And it had also been suggested that the liquid, if it existed, may even be superconducting, but let's not go there. The other example is about the phase diagram of carbon. This is the other way around. This is temperature as a function of pressure. This is pressure as a function of temperature. This is, again, there are simulation done to determine the melting line here of carbon in the diamond phase, and also in a phase which is called BCA, this kind of distorted diamond. And there was a prediction of a triple point here and of what would happen to diamond under pressure done using simulation, and the prediction was confirmed 1 year after the calculation by experiment done in France and at the Lawrence Livermore lab by using laser shocked materials. So one interesting actually comment to make on this simulation, and that for this specific case, there has been an attempt actually to derive potentials. So people have fitted potential to specifically actually describe the behavior of the melting line of diamond under pressure. And this potential, which were fitted to the low pressure part of the phase diagram, actually performed very well in the low pressure part. But then when used to predict what would happen here, actually they did fail. While density functional theory, which of course has, within the GGA approximation, it's approximate, it has, it's not perfect, but could correctly predict actually the melting line, and the prediction will confirm by experiment.
Is there any problem of doing the simulation exactly at around 90 degrees and 90 gigapascal? That means where the curve is going towards the maxima. Is there any problem of doing the simulation and predict the result around that?
Well, there are usually problems in doing the closer you get really to the melting, the more difficult is the simulation. You always have, you cannot see this here because the graph is actually, but these points contains our error bars, and actually they are quite large. If you look at, here we have 6,000, 8,000, and so to really determine within 500K the location of the melting line has not been possible. So the closer you get to the melting line, the more difficult is the simulation. So if you wanted a much more precise determination of the melting line here, simulation would become way too long to be affordable. Another example that I just want to point out, which is also an example which highlights the success of actually using combination molecular dynamics, is the phase diagram of water that we have studied under pressure. And here, the thing that I would like to comment about is that at about 40 GPa, there are a lot of dissociation phenomena that occurs in water, right? So proton starts jumping around, and there are a lot of dissociation phenomena. And if you actually have a potential which is fitted even to the best quantum chemistry calculation ever, at low pressure, this potential will never give you correctly dissociation events. And so here it's particularly important really to have a initial molecular dynamics where at each step you compute the forces on your atom and let your system do whatever it wants to do. And so in the water and in ice, actually pressure speeds up dissociation quite a bit under certain conditions. And this happens at high temperature where quantum effects for the protons are less important, and these have been studied in a reasonable way first principle molecular dynamics. And by the way, if there are people familiar with the superionic effects and superionic solids, there is here a region of the phase diagram of water where there is a superionic type 2 convector showing up. This is a detail. Okay, this is a case, on the other hand, where molecular dynamics is not good enough. So this is a boron crystal which has a ground state. First of all, the crystalline phase of boron, which is believed to be the ground state of this element, has about 320 atom per unit cell. But what happens is that not all the sites are occupied at all times at finite temperature. If you actually try to use molecular dynamics to determine the ground state structure of these elements, you will always fail because simulation times will be too long and because you will never sample all the configurations that are relevant to solve the problem. So here you have to do something different, and actually one way to do this is to couple your calculation, your first principle calculation, not with molecular dynamics, but with Monte Carlo. And in particular here, we have actually used the first principle electronic structure calculation to come up with a Hamiltonian, an Ising Hamiltonian that we have used to do Monte Carlo simulation. But the point is, molecular dynamics can, and it has been very successful for some phase diagrams. There are systems and problems for which it's just not good enough, right? I just want to make sure that because I talked about successes, we don't extrapolate and think that we can always use molecular first principle and be successful. So this is a totally different type of problem, so that one may want to solve by using first principle molecular dynamics, and is looking at a liquid. This case is water on surfaces. Here are different types of examples. So this is water on a hydrophilic surface. In particular, this is silicon carbide. This is water confined between graphene layers. This is water in nanotubes. This is water around benzene, and these are examples of ions in water. This is an interesting example because it highlights two things. One, again, if you wanted to do this kind of simulation by fitting potentials, it would be extremely difficult because every time you change the surface that your water is in contact with, you would have to refit everything. And these are complex systems, right? You have the water or the carbon, silicon carbide, and so on and so forth. So again, this is an ideal case to use ab initio molecular dynamics. On the other hand, this is also a case where that highlights some of the limitation of the theory that we use. There are certainly issues in describing accurately the interaction between water, for example, and graphene, because of some dispersion interaction that may not be accounted very accurately within density functional theory. And so it's an ideal case in the sense that we don't have to fit anything. We have something that we can, a technology that we can use to look at different surfaces, but in the interpretation of the results, we need to be careful because we can only be we cannot be fully quantitative because of the theory that we use, the theory underlying our first principle molecular dynamics. And I just want to give you an example of the kind of questions that, for example, you may want to look at. If you have water on your surfaces for a number of problems in nanoscience, for example, an interesting question is to understand whether the properties of what happens at the interface are just determined by the fact that you have your surface or your water, or also depends on whether your water is confined between two interfaces at a different distance. And then there are fundamental questions about what is really a hydrophobic interaction. Can we really treat a hydrophobic surface as a hard wall as many people have done for many years with potentials, or will there always be some electronic effects that actually hamper the treatment of this as a hard wall, and this is much more complex? By the way, this is a fundamental question in all the simulation of proteins, for example, that has nothing to do with material science, where hydrophobic interactions are believed to play a very, very central role. They are all fitted by standard Lennard-Jones potential. But if you then look at systems that are much easier and much more simple than proteins, like a graphite substrate, and you look at the interaction between your substrate and the water, you realize that you cannot really treat this as a hard wall. And so possibly also when you go to more complicated systems, this is not going to be true. So this is to give you an example of the use of this simulation to solve material science problems like this one, really looking at the interface and looking at what happens, but also at solving like fundamental problem about what are we talking about when we are talking about hydrophobic interaction. And these are all over the place involved in the solution of many problems. So this is my last example, and it's again a different kind of a problem. And this is the use of molecular dynamics to look at nanostructures. And here is a piece of work where we have actually used first principle molecular dynamics to look, you put some carbon on an iron catalyst, and you basically, unfortunately, the movie didn't work last night, and so I'm not even trying right now. But you look at how the carbon nanotube may grow on an iron catalyst, and actually you can compare with the experiment. And there are quite a number of things that you can understand. You can understand, for example, that your nanotube grows capped. And you can also understand that there are conditions under which your nanotube may grow without the presence of a supersaturated solution. So why is this important? Because this tells you about the experimental realization of the growth of these nanoparticles. Okay, so I hope this gives you an example of what you can do, and the fact that there are very many exciting problems that you can deal with in molecular dynamics. There are many other exciting problems that are completely out of reach of first principle molecular dynamics. This is one that we discussed with some of you actually at the break. For example, suppose you want to actually deal with nucleation processes. This is one of the simplest ones. Nucleation of silicon from the metal in the presence or not of a surface. Suppose that you want to nucleate a nanoparticle in a matrix. This is actually a very important problem for all the people that are trying to understand what happens when you precipitate a nanoparticle in a matrix and you want to see if the nanoparticle has some specific lasing properties. There is a lot of cooking going on in the experiment, but no good structural model. These are all problems related to nucleation processes. These are totally out of reach. These are simulations that requires systems of at least 10,000 atoms, where you have to use accelerated MD techniques implying simulation times of nanoseconds for many, many runs. And so these are totally out of reach. And and this is also in a way related to another topic we discussed over the break with some of you. For example, if you want to describe rare events and you want to use advanced simulation techniques for rare events, it is still very difficult to couple those with first principle molecular dynamics. And so these are all kind of systems that you are able to deal with only with empirical potential, with all the limitations that go with that. Okay, so I hope I gave you an idea of what molecular dynamics is, and also I gave you an idea of what the problems that you can do with ab initio molecular dynamics. I didn't tell you really how to do an ab initio molecular dynamics and everything one needs to know in general, and also in particular if you want to go to large-scale calculations. Some of the calculations that I presented, especially the one on water, could be done only on high-performance computers, and they do need they require the use of parallel code, then you will hear this tomorrow. And this afternoon, there will be actually exercises on ab initio molecular dynamics, and we'll start from very simple models.